thanks, Emmanuel, for this great opportunity. It's been a pleasure, being here with you. As you mentioned, my name is Ibrahim Sabek. I'm currently a postdoc at MIT, working with Nebraska and Mike Cavarilla. And most of my work focus on exploring the machine learning for query execution and scheduling in general. In my talk today, I will focus more on query scheduling, sharing with you some recent research results that we have been working on for a while. This is a recent paper that has been accepted and will be published in Sigma 2022. And with being this, I'm gonna structure my talk as follows. I'm gonna start with a bit of overview of the query scheduling problem, existing scheduling solutions, and limitations of these solutions. After that, I'm gonna go and give some details about our system LSched. And finally, we'll be sharing some interesting results that we have from our experimental evaluation of LSched with different benchmarks and compared to different baselines. So let's get started. So what's query scheduling? So query scheduling is typically as a task of deciding when and how the DBMS execution engine will execute the existing queries that we have in the system, with an objective of minimizing the overall latency of the existing queries that we have. And as an example here, on the right part of the slide here, we have two simple join queries, Q1 and Q2. The DBMS will generate a physical query plan for each one of these queries. As you can see, each plan will have different set of operators. They are highlighted here in different colors. And these operators will be executed eventually through the execution engine. Each one of these operators will be having a set of work orders. And you can think of one work order as an instance of the operator logic that has been applied on a certain data segment or a certain data block. So these work orders can be running in parallel. So once we have these query plans with a set of work orders that we have, we send this information to the query scheduler and the DBMS, and then we get a certain execution order for executing these plans according to a specific scheduling policy. And then once we get this execution order, we pass it to the query execution engine with the different query operators and work orders that we have to get the operators actually running and get the actual output at the end. And as you can see here at the very bottom of the right part, I'm just showing here a simple visualization of the execution order of these two operators plans that we have here in the two queries Q1, Q2. During running them through pipe execution threads, as you can see here in the vertical line. And the x-axis here is showing just the timeline for the execution through each one of the threads. As you can see, each row here is just showing the progress of the execution of the operators in each one of the threads. So why not just using the operating system to schedule the queries that we have in the DBMS? Actually, this happens in some DBMSs. And for example, Postgres is a well-known DBMS engine, and it actually creates operating system threads and processes for new connections. And these connections will be handling the incoming requests or incoming queries in an isolated fashion. So it just relies on the operating system to run this. However, just relying on the operating system to schedule stuff is not optimal, because the operating system ignores the characteristics of the database, what actually the tasks are that we have, what are the operators, what are the execution plan that we have. So basically, just abstract the execution unit as one thing or one item that need to be run through the operating system processes or threads. And on the other hand, DBMS knows much more than this about the task. They know exactly what are the tasks that we have, where is the data located for each one of them, how much thread should be assigned to each query operator or query plan, is a data cached? The data in the cache also warm or not or cold? So we have so much information resides inside the DBMS about the query execution plans. So it makes sense like the DBMS to take over the task of the query scheduling to have efficient execution time and day. And this is exactly the reason for having the query scheduling as a core component in many DBMS systems, both commercial and open source around us. Examples include here IBM DB2, Oracle, Microsoft SQL Server, MySQL, Opera, and the list goes on. So we have so many, system that has this query scheduling as a component inside. So if finding and if, yeah. There any question? Okay.
Do you have a question?
Yeah, no, I just thought like there is a question. Okay, so I'm gonna move on here. Finding an efficient query scheduling, policy is in general a hard problem, and it's not feasible for some scenarios. For example, if to have a very efficient like DBMS query scheduling policy, you need to consider a lot of factors. So, for example, that scheduler needs to be aware of the operator types, the details of each operator, the characteristics of these operators. Even if two operators do the same job, for example, a join operator, the implementation details of each one of these operators does matter. So, for example, if we have a hash join, if you have an indexedness loop join, so the details of these operators will be making a huge difference in the query execution and the scheduling as well. Operators pipelining is a very important and crucial factor. The scheduler needs to be aware what are the pipeline breaking operators and non-pipeline breaking operators in each query plan, how they are scheduled to have an efficient query execution at the end. Also, as we're gonna see later, finding the suitable amount of pipelining, not extremely doing the pipelining all the time, or not just ignoring the pipeline all the time. The suitable amount makes a huge difference in the execution time, and so on. So we have so many characteristics that and factors that we need to consider when we do the query scheduling, especially in the relational database systems. And finding an optimal scheduling policy is very hard. Just an example here, scheduling n queries on m threads or cores just to make the make span of the schedule is very minimum is proving to be NB complete. So this is just one factor that we consider in the query scheduling. Imagine now if we add more complicated factors to this, so that the scheduling policy could be very, very complicated to achieve. So as a conclusion here, for this part is that query scheduling is an important problem, but it's a very complicated problem, and we need to take care of. So existing scheduling solutions can be categorized into three main categories. The first category is a heuristic-based category that we have here. Different scheduling policies, just algorithms, and these algorithms are just based on guidelines, easy to implement, but they are ignoring most of the DBMS-specific scheduling factors that we just talked about. So we don't know about the workload-specific stuff, the pipelining degree, and all the factors that we just mentioned as an example. Another limitation in this category also is that some of them require to have manual tuning. They have complicated configuration. For example, in the highest priority first job scheduling policy, we might need the user to spend some time to tune the different templates of queries and sub-queries that need to be having a high priority, so that the scheduler can start taking into account these priorities while doing the scheduling operation. So sometimes some of these scheduling policies need to be tuned as well. Another category is just sticking to the to the same heuristic-based scheduling, but now we do the tuning of the parameters automatically. And some recent work here, this is a very recent work, self-tune, is just showing a query scheduling for on-prem system based on it's using a priority-based scheduling policy, but now the parameters can be tuned according to the workload that we have. but still we have the same strategy or the same logic in the scheduling algorithm. So they still ignore most of the DBMS specific scheduling factors. The third category that we are interested in, and we think this is like, the more sophisticated one, is to learn an end-to-end scheduling policy, which is complicated, but could be much efficient than the heuristic base. So this policy could be combining like some of the heuristic-based policies together. Could be like creating a new one from scratch, and so this will be something that's very complicated and doesn't have like a specific pattern in it, but it could be very efficient. And the state-of-the-art technique in this one, in this category, is decimal system. This is a system was proposed by some colleagues of mine, like in MIT in SECOM 19, and they just use showed that you can use the machine learning to leverage the information that you have in the system so that you can get one complicated scheduling policy that abstract the system state or the query state that you have. But the problem here in this category that they are not specifically the factors that they are talking about here in the paper or the approach based on, it's not specific for the DBMS. They just use abstract level system, Notion. For each task, they just have the execution time, the amount of memory used for each task, but they don't know exactly for each task what's the operator inside it, what's happening, how the relations between the different operators can affect the scheduling. So it's still missing the piece that we are looking for a relational database. So a natural question here rises, since there are numerous competing factors that we mentioned, and all of these factors cannot be handled by human experts, of course. So can we use a similar approach, learned scheduling, to have an end-to-end query scheduler that considers most of the factors that we want to consider here, or at least most of them, not considering all of them if this is not the case. And the question is answered by our system. We propose here LSched. This is a learned query scheduler that can support scheduling the operators within one query and also across different queries. We focus on dynamic analytical workloads because this query scheduling will be very important for this, but the query workloads and analytical databases will take so much time, and improving or scheduling them in an efficient way will make a huge difference in the overall execution time at that. But before getting into the details of the system that we have here, I'll just show you here a small example on how considering the DBMS specific factors while we do the scheduling, like in LSched we propose here, can improve the execution time. In this example, we have a simple query that has 6 operators. As you can see, they have different colors. Each one of these operators will be annotated with the number of work orders that need to be done inside it and the duration of each work order. And as you can see here, we have here 2 pipelines formed from this query. The first pipeline is 01, 02, 03, and the second pipeline is 04, 05, 06. And as you can see here, we have a pipeline breaking between 03, 06. This is, if you think of this as an example of join, this 03 and 06 will be the 2 parts that implement the join. The 03 could be the building hash table operator, and 06 will be the probing hash table operator. And in this case, we cannot start the execution of 06 until the execution of 03 completes. So all the other operators can be pipelined, but this one cannot. What we are going to do here is that we are going to show the scheduling execution order for 3 different schedulers here. A heuristic-based one, which is the critical path, decimal, which is the learned one that we have till now, and our proposed system, LSched. And in this example, just like to recap it here, we are just focusing on 4 aspects to be considered when we are doing the scheduling. The first one is considering the number of threads, and the number of work orders in each operator, and also the pipeline nature that we have here, in the queries that we have. So for the first scheduling policy, as you can see, we have 5 threads, and now we are going to start doing the scheduling using them. So in critical path, we just run the heaviest path, or like the heaviest pipeline first. So in this case, we are going to run the pipeline 1. As you can see here, the number of resources that we need for each one of these operators are available here. They are available. So we have a total time for this pipeline is 50. But now since O4 is independent of O3, so we can start overlapping the execution of O4 and O3 if we have the resources for O4. And this is a case here. We have here O4 can be running with O3, and then the whole pipeline after that can be running. So the total time for running this scheduling policy will be 25. But now here we run the maximum pipelines for everyone. So in the second policy that we have here is in Decima. So in Decima, we use the same query, but now Decima is not considering the pipelining, the DBMS pipelining characteristics that we have. So just abstraction. It can run any operator as long as all the parents of this operator are already done. So for example, if we start here at the beginning, we have O1 and O4, so we can schedule them in parallel. And then after we finish this, we have O2 and O5, so we can start scheduling them. And after that, we have O3 and O5, but now they have a pipeline breaking mode. So we can run them only sequentially, as you can see here. And the total execution time for them will be 25. So here, this is another example that it learns how to, for example, it learns how to pick the most efficient, the most important operator to be scheduled, but now they are not considering the pipelining of it. Now the last example here, the LSched. So now what happens here that we learn the scheduling policy, but now considering the DBM, the pipelining mode. So here we start with O1 and O4 scheduled as in Decima, fine. After that, we have O2 and O3 can be running in a pipelining mode. So this is a difference from Decima. So here we can run this in parallel with O5. So this makes a huge saving in the time here, because now we can run O5 and O3 in parallel, because now we start scheduling O2 and O3 together. So now O5 can be running also with them. And after we finish them, we can run O5, and the total time here can be saved will be 20. Here, the total time is 20, and we saved five time units. So in LSched, we use the proper degree of pipelining, but in critical path, we use the maximum pipeline. In Decima, we use a non-pipeline. So this is an example of considering the database characteristic in the scheduling here. And imagine here that we consider other factors, how much saving could be having here. Of course, it's a very complicated, but this is just a toy example to show the benefits that we have. So LSched in general has 4 contributions. So the first contribution is it shows for the first time that we can use reinforcement learning efficiently in the context of the analytic database systems to build workload-specific query scheduling. And in LScheduler, we don't use off-shelf reinforcement learning as is. We customize it so that we can make the case of the case scheduling applicable in this case, because we have some characteristics and details as we're gonna show here that could be different. The second contribution that we have here is LSched is having new query encoding techniques that can efficiently represent the state of the information that we have in the query execution engine and the workload, and they can help us to scale up the performance of the scheduling policy. We were going to also show some details about this part here. The third contribution that we have here is that LSched can support optimizing a query scheduling policy that can minimize both average and tail query latency. So we are not looking only for the average cases, we also take care of the extreme query cases that can be running for a long time. And the final contribution that we have is that LSched is equipped with an effective training phase that can avoid starting the training of a new scheduling policy from scratch for every workload. It uses the transfer learning to to transfer the information that can be common between different workloads, along with some of the efficient distributed training phase that we have. This is a secret sauce here we also use in our system. So by leveraging this, we have like a small training phase and efficient one for different workloads. As a head results here for summary results for LSched, we improved over the performance of existing state-of-the-art query schedulers and heuristic-based ones with at least 35% and 55% in both streaming and patching query workloads. And here we are mentioning the percentage and improving in the average query latency. So LSched can improve 35% lower average query latency for the two types of workloads that we have, streaming and patching. In the talk here, we're gonna give more details about the first two items or the first contributions, the first two contributions that we have, and the last two ones will be available as a details in the paper when it's published. Okay, so before we start here the different parts in LSched, why we picked up the reinforcement learning to build the LSched. We actually thinking a little bit about this. We have like a larger space of supervised and unsupervised machine learning approaches around us. And we found that reinforcement learning has two main advantages, which they are common for every problem, but they are also true in our case. So the first one is that reinforcement learning, it allows us to have a corrective feedback loop. And this is very efficient to improve the quality of query scheduling over time, especially if you have long time running workloads and there is a shift in the distribution of the workloads over the time and so on. So we need to have a corrective feedback loop so that we can make the query scheduling work in an efficient way. The second approach is that, the second reason here, I'm sorry, for that the feedback here that we have is only available after a series of scheduling decisions. So after running patch of queries or a set of individual or streaming queries, we can get some signals about the query latencies of this different queries. This is actually practical because you don't need to overwhelm the DBMS system by sending signals after each query, you finish its execution so that you can update the models that you have for the query scheduling. No, it's not practical at all, but the reinforcement learning is really efficient in handling the rewards over an episode. And this situation is investigated in many approaches in reinforcement learning. So these are the two main reasons that we found that reinforcement learning will be desirable for query scheduling in our case. And here, LSched is following a classical reinforcement learning framework, but with, of course, different details. It has two main building blocks in any reinforcement learning framework. It has environment and it has agent. And the environment in this case is a DBMS execution engine that we have. And the scheduling agent will be the models that will be used for learning the scheduling or updating its parameters and so on. So, once we have a scheduling event is triggered, let's assume that we trigger the scheduling event whenever we have a certain thread available or a user query comes, a new user query comes. So now the system here will take the queries that we have and generates physical query plans to it, and then send these plans along with information about the execution engine to the scheduling agent. Then the scheduling agent will like take all this information and digest it to have a state representation, and then this state will be used to predict the scheduling decisions, which is the execution order that we need for the execution engine to run the operators that need to be running. And we send this execution order to the environment back, and after the execution finished, signals about the query latencies will be saved in the experience manager, so that when we finish like in a certain episode, or we need to retrain the parameters of the scheduling agent, we can use this experience that we stored there to update the parameters of them. So as you can see, this is like a classical reinforcement learning framework, but the details here in the query encoding, the scheduling predictor, and the execution, the interaction with the execution engine is different. So any typical problem needs to be represented by reinforcement learning. We need to have an efficient MDP representation for it, the Markov decision process representation. And this actually spans 3 items: the state representation, the action representation, and the reward representation. But before we talk about this details in LSched, we need to actually make the assumptions about our system. So in our system here, we focus only on multi-threaded single node in memory analytic DBMS. So we don't have distributed cluster. We just have one single node, but this node can have multiple threads to run the different queries. This is a common setup in many in-memory analytics DBMSs. So it's nothing like unorderly. And we focus here on the threads as the main resource to schedule. Of course, our approach can be extended to to schedule the CPU cycle, for example, the memory budget or whatever. But we show here as a case study the threads. So in this case, the state information in our system comes from both the query plans and the execution threads that we have here. We're going to see an example on how they are interacted to generate an action space. As you can see here, this action space is basically the assignment for the operators at the threads. And of course, here we are using a reward for updating the model that we have based on the query latency. So to give a concrete example here on how the state and the actions are constructed in LSched, assume that we have here 2 queries, Q1 and Q2. And these 2 queries should be scheduled over 3 threads, T1, T2, T3. We can think of the MDB in the initial state that we don't have any of these queries executed, and also we have all the threads are available. So now we can we can trigger a scheduling event, and this scheduling event will be once it's triggered, we can have an action space based on the state that we have here. So we can see here that action space has 2 dimensions. The schedulable items, this is the first dimension, and the second dimension will be the available threads that we need to assign to these different items. And the action space will be depending on the current state that we have. So for example, here, as you can see, in the available items to be scheduled here, for example, is this operator, or also this pipeline, and also this item could be this operator. This one, these are the different examples that we can have for schedulable items. And here we have different combinations of the threads that we can assign to each one of these items. For example, we can assign only 1 thread, we can assign 2 threads, we can assign 3 threads for any one of these schedulable items. So as an example here, let's assume that the scheduler will be picking one of these scheduled items, which is this one, the pipeline here, and then it will use this schedulable item to predict the number of threads that needs to be assigned to it. And all of these predictions will be based on probability distribution that is estimated by the neural network of the query scheduler. But we are like just not talking about the details at the moment. We just like assume that given the predictions from the scheduling agent, we pick these items and we pick these available threads. Now we assign these items to the threads and we mark the threads are busy. Now we still have one thread which is still available for scheduling. Now we pick from the remaining schedulable items in this action space, one item, and then we assign the available thread here in this case. So once we have all the threads are available, now we don't have any actions to be sent, like new actions to be sent or new scheduling events to be triggered. If a new query comes, like Q3, we'll still not be running it now till we have available resources for it to be. So we don't have any preemption or moving operators from one thread to another. So once we are done with, for example, here the first item, which was running like on the two threads that we have T1 and T2, now we can schedule another item. Now the action space will be different because now we have new items coming from the new query, and now we picked here from the available threads. Just note here that we still have T3 busy with the assignment from the previous state, so we don't touch the thread here. We pick just from the available threads that we have. So now we assign this to the two threads that are available, and we do this so on until we finish the query execution for the different items that we have. So now once we have all of this, resources are empty and we don't have any queries, now we reach the terminal state. And in the training mode, we call this as an episode. So once we finish this episode, we can use the rewards that we gathered through this episode to retrain the model if we need. And here the reward is minus the latency. So now we will assign a reward for each executed query. So for the features that we are using in LSched, we are relying on operator level features, edge level features, and also query features. For the operator features, we use the operator type, the operator connectivity within one query, and also the input relations, the columns that will be accessed in this operator, columns, of course, of an input relation, the number of blocks or the description of the blocks that we have, the description of the work order and will be accessed during the execution. And at certain scheduling event, which will be triggered at any time, we also estimate the remaining work orders, the estimate duration, the estimate memory for each operator. So we have a specific features for each operator, which is like very, very low level details here. And also the edges between the operators, we just to get the information about the pipeline breaking mode, pipeline direction, what are the source and destination operators in each plan, and so on. Also, beside the low level information that we have on the operator and the edge feature, we have also a query level features like the assigned thread, the thread locality, which operate a map that shows which operator is assigned to which thread, so that we can improve the data locality, for example, or NOMA awareness, something like this. So all of these features will be used to generate the state and continue the process of the scheduling that we have. And as you can see here, we have two types of the features. Static features, as you can see, operator type, operator connectivity, input relations, columns, blocks, and the edge feature is also pipeline breaking. By static features here, we mean that these features are generated only once we have the physical query plans coming from the query optimizer. So nothing will be changed during the query execution. And dynamic features are features that will be changing whenever we have a certain operator finished or a query is executed. So these dynamic features will be actually capturing the current state of the execution environment. So we rely on these two features, not just a static features, so that we can capture the current state. Now we move to the most important part in the LSched, which is the query encoding. Of course, once we have more tons of information from the features coming at the level of each operator for hundreds of queries around us. So we have tons of information we need to efficiently digest so that we can, build a state information out of it. And we do this by encoding. Of course, encoding is a process of learning an efficient representation, just an embedding vector. And one straightforward way is to build one for each query, for example, or for each operator, we can just build one large fixed vector of embedding, for example, for one query that captures all the information. But this will be very hard because the large vector will be hard to be to be easily processed in the computation of the neural network, and also it will not be capturing the details of each part in the query. So just one fixed vector will not be the best solution. We rely here on a set of small embedding vectors at operator level, at the edge level, and they are easy to be generated and used during the scheduling decision prediction. So of course, we generate this embedding vectors also using neural network, but neural network design actually doesn't matter when you implement or generate the embeddings here in our case. So one straightforward approach is to just use a neural network as a black box, just run a fully connected neural network to generate the embedding vector for each part in the plan. But this is suboptimal because the inductive bias of the fully connected network is very, very low. So it's not capturing the main characteristics in a good way. It's not capturing the intuition behind the shape or behind the kernel that we use. And for who doesn't know so much about the inductive bias is a measure for how the convolution kernel that you use is matching an intuition. Like for example, in the CNN, you have this rectangle convolution filter, and then you you just pass it, or you slide it over the image, and this actually maps what happens in in the human eyes, and also capture the spatial locality, and it has an intuition for how the items or the pixels are capturing characteristics features from its neighbors. And the same thing here for hierarchical. If you have a tree convolution, you can capture the hierarchical traversal over this DAG or whatever, using a tree kernel and so on. So we have here, in our case, we have studied 3 different alternatives for the neural networks: the fully connected, the graph convolution, and the tree convolution. The fully connected, this is the default one, and the graph convolution is used in decimals. That's why we wanted to investigate it first in the beginning. And tree convolution is actually proven that it's good in the context of the relational queries processing, and by some previous work by our colleagues for query optimization and so on. So we actually found that the results that we got matched the recent research results coming from Google Research 2018, that here fully connected and the graph neural networks, they have non-desirable inductive bias in our case. So for example, in fully connected, it has very weak inductive bias. In the graph neural network, it has a randomness because the information is digested from the different neighbors in in a manner that you can have like, I mean, higher noise, or noise can be propagated over the difference. So this like encouraged us also to use the tree convolution inside the graph, like instead of the graph convolution, especially because we are using relational queries. And I'll give you an example of why this is like, I mean, using the tree convolution network is better than graph convolution. Assume that we have this query with 4 operators, as you can see. And in each operator, we have only like, I mean, feature vector of 2 items that represents whether this operator type is indexedness loop join or a scan, like a scanning index. This is like, I mean, a scanning or an index loop join. And we want to, like, I mean, capture a pattern for indexedness loop join over a scan, like over the scan operation. Like, I mean, whenever we have an operator, a child operator of indexedness loop join, we want to see if its parents can have a scan index or not. And we can do this in graph convolution and tree convolution network in 2 different ways. In the graph convolution network, we can just assign weights for each one of these features. So if we have here a node that we want to detect if it's an indexedness loop join, we just have its weight to be positive and the other will be negative, so that we can punish the calculation moving forward when we do the convolution. And for the tree convolution here, we have more accurate representation. We can like specifically assign weights for indexedness loop join different than the ones in the scan to capture each one of them specifically. And as you can see in the graph convolution here, the way that we calculate the embedding at each item, it's just we like, I mean, apply the weights that we have here from the graph node weights on the left part here. And we apply these weights on the node itself, the feature vector on the node itself, and combine this with the information coming from the children. In this case, we have a DAG, so we have only information coming at each node from their parents. In this case, for example, O3 will have information coming from O1, O2. So in the beginning, if we want to, like, I mean, calculate the embedding here at O1, we don't have any parents, so we just update the feature vector here with the weights. We have this, and we do the same thing for O2. And once we move now to O3, we have different parents. So now we combine the updated feature vector with the weights here with the information or the embeddings that we just calculated at the parents. So we have a different embedding here at O3 and so on at O4. In the tree convolution case, it's different. We just apply the filter on the different operators that we have. Whenever we have a filter applied at a parent or at a certain node, we just match that tree shape that we have with a hierarchy that we have here from the query plan. So for example, here in the beginning, O1 and O2, they don't have any children, they don't have any parents, sorry. So we just update the embedding of O1 or calculate the embedding of O1 with just the parent node that we have here. And similarly for O2, we just use the parent, like the parent node here in this triangle. And once we move to O3, now we can use the whole shape of the tree filter to combine the information that we have. So we just calculate, we just multiply the different embeddings at each, or like the different features at each node with weights that coming from the corresponding node in the tree, and so on. So now we have completed the embedding process. So now we see here, we have 2 different embeddings from graph convolution neural network and tree convolution neural network. As you can see here, we want to get an intuition which one is better. So it should be the one with the higher positive one, the higher positive values of embedding should be the better here, because this should be matching the filter that we are using for convolution. So if you see here tree convolution and graph convolution embeddings of O4, we can see here that here it's more positive values compared to the one in the graph convolution. And the same thing here for O3. You can see these are more positive values than in O3 here in graph convolution neural network. And this actually makes sense because here O3, from the feature vector that we have here, that it's an indexed nested loop join defined over 2 scans. The first item is indexed nested loop, the indexed nested loop join, and the second item will be scan. So O3 should be higher in its positive embedding values than O4 because it has here 2 scan indices that, like in the parent here, that increase the embedding value. So tree convolution neural network captured the embedding values that we need better than the case in the graph convolution. In order to improve the performance of the tree convolution neural network that we use here in the query scheduling, we combine this with the graph attention networks, where we the graph attention, we just have an importance weight for the different filter weights that we have in the tree convolution. So, for example, this filter doesn't have any importance weights on the edges or nodes that we have here. But now, on the right-hand side here, we have importance weights, 0.5, 0.1, 0.1, 0.1, 0.2. So this means that all the information coming from this node will be weighted with this importance value when we calculate a certain impact. And of course, these weights are not static; they are learned, during the scheduling model building that we have with the neural network. So it's trained inside that training model the training phase that we have in the scheduling. So once we are done with the single query encoding, we have for each operator we have a certain embedding vector using the tree convolution network combined with the graph attention network, and also at each edge. Now all of this information will be combined on 2 steps. The first step is on the query level, and the second step will be across the whole queries. So we have per query embedding, and we have also all queries embedding. But the details of this summarization or high-level encoding are kept here. It will be in the paper. So now we have 3 different levels of information: embedding vectors at the operator level and the edge level, embedding vectors summarizing the whole information of one query, and embedding vectors that summarize all the information across the whole queries at a certain moment of scheduling. We have here 4 scheduling events that we we design LSched around. When we have a new thread returned or added, for example, if we have an execution pool, and once a thread is free, we trigger a scheduling event so that we can do a scheduling decision. This to avoid any idle resources to be there. And also the same thing here when we add a new thread, just a new thread will be added. So we also trigger a scheduling event. Also, whenever a new query comes to the DBMS, also if we have available threads or we have available resources, we can also initiate a scheduling event. And also when a certain operator with all its work orders finished, so now we have a room on a certain thread, so we can also schedule it. Just the scheduling decisions that we have it, just I gave you here a hint on how they are calculated. Basically, we have 3 decisions that we make at a certain scheduling event. As I showed in the example of the MDB, we first choose which operator to run, and this comes from a neural network. So this is a probability distribution that we use. We calculated from a fully connected network. All of them are calculated from fully connected network. The inputs here that we have to this network is the embeddings coming from the tree convolution and the query encoding that we have on all levels, the query encoding, the bare query encoding, and all the query encoding. once we have an operator, we decide two other things. How many operators to pipeline starting from the operators that we choose now, like whether we are going to do pipelining or not. And the other thing, like how many threads we need to assign for running the queries that we have. So these are the three decisions that we take at each scheduling event. And we keep doing this, ask which operator, which threads will be assigned, and so on, until all the resources that we have at a certain scheduling event will be, all used. Then we stop the scheduling decision process, and then we send the execution order. As just small summary for the evaluation results that we have. We evaluated LSched with the 3 workloads: TPCH, SSP, and job. And in each one of these workloads, we generated a certain training data set and a certain testing data set with different arrival rates to simulate the queries coming at different rates, and also the patch of queries that we can use. And for each one of these workloads, we compare the performance of LSscheduler with a bunch of systems that we have and the scheduling policies that we have. We compare this with Decima and with Quickstep, with Self-Tune, and 2 heuristic approaches, FAIR and FIFO. So Decima, this is a learned approach that we are comparing with. This is a state of the art of the learned query scheduling, but now without any optimization for the DBMS. The Quickstep is a well-known open source analytic database system, and it has support for query scheduling inside it, and also has some learn or tuning version of the query scheduling. Self-tune, we got the source code from the authors, and we try to adapt the workloads that we have here to run and regenerate the results that we have in SIGMOD and their paper in SIGMOD. And as you can see here, when we compare this with this system with TPCH in both streaming and patching mode. In streaming, we have queries coming at different arrival rates, so it's not a patch. In the patching, on the other hand, we have all the queries coming at a certain time, but here we have different number of queries. As you can see here, this is a CDF of the average query duration that we have. The hard blue one is LSscheduler. We have the least average query duration in both streaming and patching. You can see here, heuristic approach like FIFO is the worst by 4. And also a small observations that we saw and noticed in all the benchmarks that we have, or the workloads that we have, that in patching mode, we have a better performance again over others, because in patching mode, we have so many queries coming at the same time. So we need to schedule all of them together, and the resources of the system will be overloaded. So the quality of the scheduling approach will be making a huge difference. So in our case, since we are carefully learning how to schedule them, we are making much better performance again compared to the streaming. This also is confirmed also when we run in SSP benchmark, and also in the job benchmark. And interestingly, in the job benchmark, we have also better performance again. And this is expected because it's a more complicated workload. It has queries, some of the queries have more than 10 joins inside it. So operations are very expensive, and also they have some correlations among the different items in this workload, like different queries and different items we access. An interesting and important experiment here is to measure the scheduling overhead. And of course, the learned schedulers like LSched and Decima will be having much higher overhead compared to all the other heuristic based, because we have an overhead for the computation of the neural network operations, for doing the inference, we're doing the updates, this kind of operations. So it's a very, very high overhead. However, which is important, that the performance again we get even with this high overhead, is much, much better than this. We have also almost 100x, time saving, the time saving is 100x than the overhead that we have in the learned schedulers. So it's still very efficient. Yeah, of course, we have an overhead, but it's still very efficient in the case of the analytic workloads because it takes so much time to run. Of course, approaches like LSched and Decima, they are not working very well, and OLTP transaction projects, they are very small, and the query is very, very small and light, and we don't need to have very complicated overhead to add. But in analytical workloads, we find that the learned scheduler is an efficient idea that's worthy to investigate. We are as a detailed investigation for the performance of the different parts in the system. We show here different variation of LSched without different properties in the system. For example, here, if we just not using tree convolution and we use the graph convolution, we can see here that this is the most affecting parameter or the most affecting property in our system. The execution time has been very, very bad compared to the original version of the system that has all the properties. You can see here, this is only the effect of the tree convolution. The second most affecting factor is also using the graph attention, which is here also. After that, the effect of the transfer learning and the effect of the pipelining, it's still making a difference, but not that much compared to the effect of using the tree convolution and the graph attention network in our case. By the way, this result is using the TPCH workloads. So, and we matched the same results in the different benchmarks. So as a conclusion here, learned query scheduling and analytic DBMS really matters, and they perform much better than the heuristic-based approaches. And LSched is showing a first prototype for doing this in the query scheduling part. Of course, the idea of using reinforcement learning and other machine learning has been investigated in query optimization and other parts, or database tuning and other system components. But for the query scheduling, we were the first to show its effectiveness in analytical workloads. And performance, again, is still considerable, improving around 35% and 50% for large query workloads is actually something that we consider. And with that being said, I don't have any more thoughts to share with you for now. But of course, if you have any questions, I'm happy to take it now. And if you prefer to send me over email, I'm also fine.
Awesome. Let's thank the speaker already.